In this presentation, we're going to talk about the first shifting theorem. Now, in the previous lecture, we introduced the idea of a Laplace transform and we showed how to calculate some of the basic transforms using the definition, and we also learnt how to use a table. So in this lecture, we're going to see how we can use the following theorem, the first shifting theorem, to help compute Laplace transforms and their inverses. So just to refresh your memory, the Laplace transform is an integral transform, and it's denoted either using this curly L or this big F of S when I have a lowercase denoting my original function of t. And essentially the definition involves an improper integral, so you take your original function, little f of t, multiply it through by this exponential and form this improper integral. Now the motivation for studying Laplace transforms lies in their application to differential equations. In particular, the Laplace transform greatly simplifies the solution method for linear DEs with constant coefficients. Okay, well, here's the table that we've been working from that we'll continue to work through. But let's quickly have a look at this first shifting theorem. Now, suppose that the function that we want to take the transform of is of this special form. It's an exponential times another function, like, e to the minus 2t times t squared. Well, if we denote big G of s by the Laplace transform of little g of t, then the Laplace transform of this form is just this transform shifted a units. So star, hopefully you can see that to compute or to use star to apply it, you first compute the transform big G of s and then you shift it a units. In other words, you're just replacing s with s plus a in the brackets here to form your transform. Well, from star, you can take the inverse transform of both sides, and it says that the inverse Laplace transform of this shifted function is just an exponential times little g of t, where little g of t is the inverse transform of big G of s. Okay, why does it work? Well, here's a basic proof. Remember, this is the definition of the Laplace transform of f of t. So let's replace f of t with this form in our integral. So I'll get this. And now this is an e to the minus st. And now if I combine these two exponentials, I get this. And this is not big G of s. If we just had an s there, it would be. But we've got an s plus a in brackets. So actually this is the Laplace transform of big G of s plus a. So let's have a look at an example. So here's a basic application. We're asked to calculate the Laplace transform of e to the 4t times t to the power 6. Okay, well, the first thing we realise is that this is actually in this form with the constant a equals to be minus 4 in this case, and little g of t is t to the power 6. So what we're going to do is calculate the Laplace transform of little g of t and then shift it a units. So we're using star here. So a would be minus 4, little g of t would be t to the power 6. So let's compute the Laplace transform of this, and then we'll shift it. Okay, so what's the Laplace transform of t to the power 6? Well, we just go to our table, we look down to the third row, equals 6, so that'll be 6 factorial on s to the power 7. Okay, and I'm just going to write down that I've used a table there. Okay, well, what we want to do now is shift this a units. So a is minus 4. So in this case, we replace s with s minus 4 in brackets. All right, so by the first shifting theorem, we have this. So for our problem, g of s plus a is just this. Okay, so that's a basic application of the first shifting theorem. Okay, let's have a look at how we can apply this first shifting theorem to another example. So we're asked to calculate the Laplace transform of this function here. Now you can see that this function here has this particular form with a equals minus 1 and little g of t equals t plus 1 all squared. Okay, so what we do is we calculate the Laplace transform of little g and then shift it a units by using star. Okay, so let's solve it. So a will be minus 1 and little g of t will be t plus 1 all squared. Okay, so what we want to do is apply the first shifting theorem, take the transform of little g and then shift it a units. That's the idea. Okay, so how to take the Laplace transform of t plus 1 all squared? Well, I'm just going to expand it into 3 terms and just do it from a table. So if I expand this, now remember the Laplace transform is a linear operator, so I can come up with the following. So now all I'm going to do is calculate those transforms individually using my table. So the Laplace transform of 1 is 1 on s, the Laplace transform of t is 1 on s squared, and the Laplace transform of t squared is going to be something like 3 factorial on s to the, 2 factorial on s to the power 3. Okay. So 2 factorial is just 2. Okay, so we've calculated the transform of little g to form big G of s. Now we want to shift it a units. Okay, so here my a is minus 1. So what I want to do is replace each s with s minus 1 in brackets. Okay. So now all we want to do is invoke the first shifting theorem. So the first shifting theorem says that the Laplace transform of this is this. So we've just calculated that. So by the first shifting theorem, okay, so the Laplace transform of our particular function is just this. Okay? So hopefully you can see a pattern emerging. Little g of t drives the method. Calculate the transform of little g of t first and then shift it. Okay? Okay, so that's a good example of an application of the first shifting theorem. Let's look at going the other way, the inverse transform. So we've used star in the previous example. Let's use this identity here. Okay, so we want to calculate the inverse transform. Okay, so we notice that actually this function has a nice form. Okay, it's already kind of been shifted. You see the s plus 1 in there. So what I want to do is identify a constant a and a function big G from that format. 1 on 1 plus 1 all squared, 1 on s plus 1 all squared. So it makes sense to let's say a equal 1 here. And if I just cover up that and cover up that, what's big G of s going to be? 1 on s squared. Okay? So from this form, hopefully you can recognise that, okay, I can come up with an a and come up with a big G of s so that we can apply our first shifting theorem. Okay? Okay, so what do we have to calculate here? Well, we want to go from here to here. Okay, so what do I need? I need a, and I need little g of t. Now, by definition, little g of t is the inverse transform of big G of s. So I want to calculate little g of t from this, and then multiply it through by e to the minus at. Okay, the inverse transform. The inverse transform of 1 on s squared, so what's that going to be? Well, if we look up our table, look down the left-hand side, 1 on s squared, the inverse transform is going to be t. From a table. So by the second shifting, the first shifting theorem, the second part, this is going to be this. So we take little g of t, multiply it by this exponential function. So for our particular question, so A is 1, this will be our inverse transform. Okay, so how do I know I'm correct? Well, I can always take the transform of what I've just produced and show that I get my original function here. Okay, so there's two ways to check this question. One would be to notice that that's just t times another function. And in previous lectures, we've worked out how to take the transform of t times a function of t. It's negative big G prime of s. Okay, I talked about that last time. So that's one way. Or the other way, of course, is to just apply the first shifting theorem to this using this star. Okay, so okay, and you show that that equals that. So this is just now I won't use oh yeah, I guess I can use G of t here. Yeah. Okay, so so I'm not going to check them, but that gives you two ways of checking them pretty quickly. Okay. All right, any other questions? Okay, apply the first shifting theorem to calculate the inverse transform of this. Now this one's a bit harder. Okay? This one's a bit harder. Apply the inverse, calculate the inverse Laplace transform, right? So we want to apply this second identity here. So can anyone suggest how we might use the first shifting theorem to calculate this transform, the inverse transform? Yeah. Now if you look closely, what we really want is a form like this up here. But it doesn't look exactly like this for some a and some big G. But what we can do is play around, and you see I've got an s minus 2 up there. What I would like is an s minus 2 in brackets down the bottom. So if I complete the square, watch what happens. Okay, so if I take out, say, if I split that 5 into 4 plus 1 and then factorise, I get that. Okay, now that form is a form that depends on s minus 2 in brackets. So it's kind of like this. For a equals minus 2 and big G will be something like s on s squared plus 1. Okay, so that's what I mean when you sometimes need a little bit of algebra to put it into a suitable format. Okay, so a would be minus 2. And big G of s, well, just replace s minus 2 in brackets with s. So I can just cover those up. I'm going to get something like s on s squared plus 1. Okay? So the first shifting theorem says the inverse transform is just little g of t times this exponential. So little g of t is the inverse transform of this. So let's calculate the inverse transform of this, and then I'll multiply through by e to the minus at. Okay, so the inverse transform of s on s squared plus 1. Well, let's have a look down our column. It's going to be something like cosine t. Okay? So from a table, so by the first shifting theorem, the inverse transform of this is just the following. So if we know what little g of t, it's cosine t. It's going to be e to the minus 2a. Let me get that. Okay, questions? Okay, so my advice is to not underestimate these kinds of transforms. People underestimate them and go, oh, look, it looks pretty easy. Well, when you're doing it, trust me, it's not so easy. It's not so easy. People struggle with these things because they don't really understand the theorems, or they get lost in the algebra. They don't really know what they're trying to calculate. Okay, so that's the first shifting theorem.